Okay, let's look at number 22. The graph of f prime is shown. We have an order pair f of 0. We're trying to find f of 1. So let's think back on something that we can use from the first theorem of calculus. We know that the depth integral of a to b of f prime is equal to f of b minus f of a. So if we rearrange that, we can say f of b is equal to f of a plus integral from a to b of f prime. So in other words, any location or final position that I'm looking for, I can always start with an initial position given, and then I bridge the gap between the initial position and final position, and I can call that displacement. So if we want to find f of 1, which is what the problem is asking for, my initial or my starting position is f of 0, and then to bridge the gap between 0 and 1, I can say integral from 0 to 1 of f prime. And to do that, we have this graph which can help us out, right? We have the f prime graph. If we want to find the depth integral from 0 to 1, that just involves the area. And this is a triangle, so we have a geometric formula for that, which is 1/2 base times height, 1/2 1 times 6, which is 3. So the depth integral from 0 to 1 is 3. So I'm starting at position 5, and I'm traveling 3 units in that same direction. So 5 plus 3 is equal to position 8. F of 1 equals 8. All right, 23. This looks like a complex problem here, but this is in the form of second theorem, which is saying that if I pair two inverse procedures on top of a function, they are, for the most part, going to undo and cancel each other out. Okay, so this is what the second fundamental theorem of calculus tells us, is that if I apply a derivative and integral on top of a function, what happens is that this upper bound variable will have some residual effect on this function, but for the most part, this function is going to remain unchanged. So the integral is going to have an effect in that p of x, this upper bound, gets plugged into the variable of the function, and the derivative has an impact in the sense that this p of x has to, the derivative of p of x will show up, so times p prime. So we can just plug in upper bound into the function and multiply by the upper bound's derivative, and that is the result of pushing both these operations on top of f of t. So if I have sine of t cubed, this process, this upper bound will get plugged in for t, so sine of x squared cubed times the upper bound's derivative times p prime, so x squared derivative is 2x, so times 2x. We have two exponents here, we can multiply them, so sine of x cubed, I can push the 2x in front, so 2x sine of x to the 6th power. All right, 24, let the function be defined by f of x, which of the following is an equation of the line tangent to the graph at the point where x is equal to -1. So if we want to find the equation of the tangent line, we first have to find the derivative. Well, let's find the order pair first. Either way, we have to find order pair and slope to create our tangent line equation. So to find the order pair, I can take my x value and put it in for the x of my function. I can evaluate the function at -1, so replace every x with -1. I get -4 plus 5 plus 3, which is equal to 4. So there's my order pair, -1, 4. To find the slope, I first have to find the derivative, so I can just apply power rule to each of these terms. I get 12x squared minus 5. 4x cubed becomes 12x squared, 5x becomes 5, 3 goes away to 0. So once I have my derivative function, I can find my slope. I can plug -1 in for the x of my derivative. In return, that number is going to refer to the steepness or the slope at that point on the curve. So 12 minus 5 is equal to 7. There's my slope, there's my order pair, and then here's the form for point slope. So y minus 4 is equal to 7 times x plus 1. distribute the 7 through, combine like terms just to make it match one of our answer choices. So we get y is equal to 7x plus 11. Okay, 25. Particle moves along the x-axis. Position is given by x of t. At what time is the particle at rest? So this is the position function given. Particle is at rest whenever the velocity is equal to 0. Right, velocity is equal to 0, that's when this particle is motionless. So we need to find the derivative to get from position to velocity. So we go through power rule. 2t cubed becomes 6t squared. 21t squared becomes 42t. 72t becomes 72. 53 goes to 0. So I want to figure out when this v of t is equal to 0. So replace v of t with 0. I can factor the 6 out. Continue factoring. T minus 4 and t minus 3. I set both equal to 0. I get t equals 3 and t equals 4. 26. What is the slope of the tangent line to the curve at the point 3, 2? I want to find the slope, which means I need to find the derivative. But to find the derivative, notice that we're not dealing with a function anymore. We have a bunch of y's inserted into this expression, into this equation. So we have to go through implicit. But there's also a hidden product rule here as well. We have two variables multiplied together. We have to go through product rule once we start this process. So each term, I'm going to find the derivative, but with implicit, we just have to realize that each time we find each variable's derivative that involves y, we have to multiply by dy dx. So let's do this one term at a time. 3y squared becomes 6y dy dx. 2x squared becomes, or negative 2x squared becomes negative 4x. 6 is a constant, goes away to 0. Now the negative 2x and y, these are multiplied variables. So to create the derivative, I have to find, go through product rule. So f prime g plus f g prime, 2x becomes 2, or negative 2x becomes negative 2. Y stays as y. Negative 2x stays as negative 2x. And then the derivative for y is 1 dy dx. So I have the derivative equation in front of me. I'm just going to clean this up a little bit here, combine some like terms. I'm going to push the dy dx terms together on the same side, the non-dy dx terms on the other side. I'll factor the dy dx out. I'll divide the parentheses over. So I have my slope formula. Once I have my derivative equation, I'm going to plug in 3, 2, 3 in for x, 2 in for y, and the numeric value that results is the slope, 4/9. Okay, 27. Let the function be defined by f of x. G of x is the inverse of f. G of 2 is equal to 1. What is the value of g prime of 2? So here's the relationship between a function and its inverse. A function and its inverse will always have these corresponding points that is going to be consistent between order pairs. So that means if there's an order pair on G that is order pair 3, 1, then on inverse of f, or on f of x, there must be 1, 3. Right? If there is 5, 1 on G of x, there must be 1, 5 on the other. So that's the relationship in terms of order pairs. So I have that in this chart here. Now, at their corresponding points, whether it's 1, 5, 5, 1, or 2, 3, 3, 2, at their corresponding points, these are different points here, the steepness of the points on those curves will also be related to one another, numerically will be related to one another, in the sense that they will be reciprocal slopes of each other. So for instance, I have a small diagram here, but if f and g are inverses of each other, there you may have order pair 1, 2 that sits on f and order pair 2, 1 that sits on g. If the slope here is 7, then the slope at the g function at its corresponding point must be 1/7. Okay, so the slope of the inverse is the reciprocal of the slope of the function at its corresponding point. So we want to find g prime of 2, but to find g prime of 2, we first have to figure out what the order pair is for the f function. So the order pair for g function is order pair 2, 1. So that means the corresponding point for the f function must be 1, 2. Okay, so I have that indicated here. So order pair 2, 1, corresponding point 1, 2. Now, if I can figure out the slope of the f graph at 1, and the reason why we're focusing on f graph is, or the f function for the derivative or for the slope, is because that's what's provided for us. So if I can find the derivative of f and find the slope of f, then I can use that numeric value to figure out the slope of the g function at 2. So here's f prime, power rule, we get 3x squared plus 1. Evaluate the slope of f graph at 1, I get 3 times 1 squared plus 1, which is 4. 3 plus 1 is 4. So if the slope of the f graph has a steepness of 4, then the slope of the g graph at its corresponding point must be the reciprocal. The reciprocal of 4 is 1 over 4. Okay, last question on the non-calculator portion, 28. Let g be a twice differentiable function. So twice differentiable function just means that the second derivative exists, which visually just means that it's a smooth curve. Okay. G prime is greater than 0, so that indicates that we have a positive slope for the graph. G double prime is greater than 0, which means that the second derivative is greater than 0 is positive, which means this graph is concave up. So maybe a portion of the graph that looks like this. Okay. Now here's something that we have to be aware of for a function that has positive slope and is concave up. The pattern that we're going to see between consecutive order pairs is that not only are we going to be experiencing positive slope if we find the slope of each of these points, but the slope is always going to be increasing. So if I find the slope between these 2 points, let's say that slope is 3, then the slope between the second set of order pairs must be greater than 3. So they're always going to continually increase in slope. So we're going to use that knowledge to help us out here. Okay. First off, we have some information about the first 2 order pairs. So I'm going to find the slope between 412 and 518. So change in y over change in x. 18 minus 12 over 5 minus 4, that's the slope of 6. So if a slope of 6 exists between these 2 points, then between these 2 points, there must be a greater slope. So I know that I put that in as a blank, right? So this unknown y minus 18 divided by 6 minus 5, whatever the slope is, it must be greater than 6. So we can just go ahead and kind of test out these values here. And it just so happens that all these values, 15, 18, 21, and 24, if we plug them into the space here, none of these will produce a slope that's greater than 6. And if it is truly concave up and positive slope, then it has to fulfill this pattern. So if I plug in 27, in for this y value, 27 minus 18 over 6 minus 5, change in y over change in x, I get a slope of 9, and slope of 9 is greater than 6. So this is the only y value that fits the pattern that will allow these 3 points to be true and to allow for these properties to exist: positive slope and concave up.